Okay, so why do we need to use chain rule? What's the occasion where we'd use a chain rule?
Is it when we're trying to differentiate like a division quotient?
No, to be honest, we'd use the quotient rule for that because it's a
Oh
division.
yeah,
Yeah, so we could end up using a chain rule within a quotient rule, but no, there's a specific time we need to use it.
right.
So Rahat, do you know?
I'm trying to remember. Chain rule.
Yep. Any more thoughts, Ollie?
Um, hmm. Just when we had two different variables in a differentiation, we need to like integrate them, differentiate them separately.
I know what you mean by variables, but I think you mean something else because we don't
Is
do.
it like one function inside of another function?
Aha, there we go. Exactly. What's that called?
Composite.
Composite, yeah, our favorite, yeah, composite functions, yeah, composite. So I was actually talking to you about those yesterday, wasn't it, Ollie? Because
Yeah.
they're nested functions in computing, so that's a composite function. So a function inside a function. It's a bit like a Russian doll, where you open the Russian doll up and there's another function inside it. Yeah, so it's usually within brackets, but not necessarily. So can you give me an example of a composite function, Rahat?
F(g) of x.
Yeah, that's true. Very general. F of g of x would be g is contained in f of x. Yes. So let's write that down. I'm not sure if you've seen that before. F of g of x. So it's written in a few ways, but if you have f of x and then you want to put g of x inside that, you write f of g of x. So g of x is contained within f of x, which is just some separate other function.
Yeah.
Okay. Your turn, Nani. Can I have a composite function?
E to the power of 2 to the x. 2x, sorry.
Yeah, good. E to the 2x. E to the 2x. So what are the two functions here that are?
So you have 2x, the power, and then you have ex.
E to the, yeah, so it's instead of e to the x in that space is a different function, 2x, yeah. Really, e to the x is a composite function because x is a function.
Right.
So it doesn't matter if it's 2x or not, e to the x is.
Yeah.
And one more from you, Rahat.
So we have e to the x. We have f(g) of x.
Yeah, you give me all the possibilities. Always good. So yeah, we could have g of f. We could have that, yeah, but specifically with some, actual function.
So e2 of x. It's another composite function.
Just think of
So
two functions and make composites of them. Yeah, so give me two different functions. Function.
Sine x plus 1.
Okay, we'll just go with sine x. So sine x, yeah. And now another function.
Cos x.
Cos x, okay. We could
I
have.
think I know the technical definition of function.
What's the definition of a function? It's just it's when you put something in for x and something for y comes out.
Oh, okay. So
Operation has happened. Yeah.
So essentially, like a quadratic formula could be a function, yeah.
Ironically, no, that is not a function. That's a
You know,
formula.
you put some values in for x, and then y comes out.
Mhm.
So why can't that be a function? It's just when you put some values in for x, and then you get the value y.
Quadratic equation. Do you mean a quadratic equation? Do you?
Yeah.
Oh, okay, so you said formula, yeah, equation. Okay, yeah. So let's say we had y equals x squared. That'll be a quadratic equation.
Uh-huh.
We could put that into the sign, so sine of x squared. Yeah, no, that's a composite function. X squared is inside, like a Russian doll. Sine of x, sine. Sorry. In fact,
Yeah.
sine x is a composite function itself because x again is a function. So sine of x is a composite function.
Okay, but you said that a quadratic couldn't be a function, right?
Well, I said the formula. So you said the formula, which is x equals minus b over 2a,
Mm-hmm.
etc. That's not a function.
Okay, no, but say if you were to write a quadratic out, so x squared minus 9x plus 2, that's a function, right?
Yeah.
Okay.
Y is a function of x there, isn't it? Because y depends on what x is.
Okay, any equation in terms of x that gives the value y as a function. Okay.
Yeah, I mean, you might suggest that the quadratic formula is a function because x depends on what a, b, and c are.
Mm-hmm.
I don't really want you to think of it like that. It's more of a way to solve a quadratic. I think of it as a function now. That's not really the right main thing to think of it as. Though technically, I suppose you could say that's what it was, but you wouldn't draw a graph of it. You know. Okay, so yeah, so there are some composite functions. So they are functions within functions. Yes. But because they're kind of inside these Russian doll function sort of things, if you do anything to them, nothing will happen to the one that's inside the Russian doll. It's kind of protected. So over times 2x by 5, the 2x doesn't get affected. It's not times by 5 as well. Over times sine x by 2, it's just 2 sine x. The x is not affected. It's not 2 sine 2x. Yeah. So paint the Russian doll outside, nothing happens to the one inside. Just stays as it is.
Yeah.
But if you differentiate them, want to find what the rate of change is, what's happening is the Russian doll inside is changing. Okay, so if you increase the size of the Russian doll inside, it's going to need some space to move into. So the bigger Russian doll changes as well. So you differentiate both of them. Okay, so that's what we'll have a look at now. Right, so let's start off with sine 2x. So I want to differentiate that. Sine 2x. So how do we differentiate that?
So we want to separate both of the functions so we can use u and v. So like let sine equal u and v is 2x, and then integrate, like differentiate them both and
So
add
the
them back.
product, essentially.
Well, just finish what you were saying, Ali, and then go in Rahat. Yeah, I didn't quite catch the end of that.
And then you kind of like use the rule to like u dv v du to add them back together.
Okay, and what did you say, Rahat?
No, so it was the product rule, isn't it? VDU plus UDV. You label sine as U and the 2x as V. You do them separately. Obviously, using the method VDU plus UDV. And that should give you the answer.
Okay, yeah. So here we have sine 2x, and we've just established that means sine operates on 2x. Okay, that's what a composite function does. It operates on the 2x. So sine, so whatever 2 is, x is, times it by 2, and then sine operates on it. And that's not the same thing as multiplied. There's no such thing as multiplying by sine, because so what does sine mean?
Well,
Height, yeah, it means height of 2x. Okay, so if x is, say, pi, then it's the height of 2 pi, the angle 2 pi. So that'll be 0. So it's just always saying it's the height of that thing. It's the height of that thing. Okay. Right. So that doesn't mean times. It means it's acting on the 2x, you know. Like, I don't know, you're doing motion, but it's kind of saying, it's just sort of saying it's an, sort of almost evaluating it, which is the height of this. Okay. So we wouldn't use the product rule because that is not a product. That is definitely not a product. It's just an operation, really.
Yeah.
So we're going to use a chain rule, which is what this lesson's about. Yeah, chain rule. Okay. So another way of thinking of the chain rule is differentiation by substitution. So
Right.
we want to differentiate both those things, sine and 2x. But the trouble is the 2x is locked inside this Russian doll. Yeah. So that's why they're not being times by each other, because it's inside a Russian doll. So you're right about substitution, but not u and v. We just need u. Just go u equals 2x. Okay. And that's one of the functions. So we need to differentiate that. So we just differentiate it.
2.
Exactly, yeah. So differentiation means d dx of the thing. So that's why the u dx. Derivative of 2x is 2, yeah. In other words, and this is an important thing to note, we discussed this last night as well, Ollie, that what does 2x look like on a graph?
It's like
the gradient 2.
Go on, Rahat.
I said a line with a gradient 2 that passes through 0.
Yeah, perfect, thank you. Yeah, so it's a straight line, isn't it? Gradient 2 looks like that. Yeah, so do we need to differentiate this?
no, not really.
No, because I already know the gradient is. You know, I don't have to do anything to differentiate. I don't have to follow a process and go, well, I'll bring the power down, take 1 off the power, all that stuff. I just already know the gradient of 2. So I just write that down. So this is why I say I never want you to differentiate a straight line, because the gradient is actually staring at you in the face.
Yeah.
2. Also, that means that this is one for Rahat only. Can you tell me what this is equal to, please, Rahat? The integral of 2 dx.
2 dx.
Yeah. What does that equal?
So is that all the area underneath 2?
Yep, yep.
Up to the point 2 from 0 to. So from all the area underneath 2. So is that referring up to the point 2 or just under the line in general?
Under the line too, yeah, that's right.
Okay, so that's the height the times the width, right? Divided by 2.
That'll be for a triangle. Just 2 dx.
Just 2x.
2x? Yeah, that's it, 2x. 2x. And anything else?
Plus c.
That's plus C, yeah, exactly. Okay. That was a bit hard fought, but we got there. Yeah. So remember, when you're integrating, you're just reversing a derivative. Yeah, something's been differentiated. If you integrate it, it returns to what it was before. Right? That's what integration can do for us.
Yeah, I didn't see the f. Normally I'd see a question with, say, a 2 at the top and 1 at the bottom saying find the area of an equation in between these 2 points. So I guess maybe that's why.
Yeah, but you need to be able to do what's called indefinite integrals, where there is no actual value. You just write the expression. Yeah, but anyway, that's not really the point, because what integration does is it returns, if it can return a gradient back to the original. So if I differentiate 2x, differentiate 2x to get 2. Now I'm going to return that 2 back to 2x, integrate it.
Mhm.
Yeah, so it goes back to 2x again, right? That's all I asked you. And you were going, but both of you really were like, ooh, not sure, right? But it's all it's, we know that integration is the reverse differentiation. So differentiation is going to give you the gradient. In this case, it's 2. We integrate 2, it's going to go back to 2x again.
Mhm.
The answer was there on the left side of the page the whole time.
Yeah.
It turns it back. Plus C. Okay, so yeah, if you can't think of what something integrates to, just think, what was it? What was the thing that's been differentiated? That's another way you could think of it. If you're trying to think what's the integral of 2, that must have been differentiated. What was it before? Oh, 2x, because 2x differentiated gives 2. And there you go, it's integrated. And so if you ever get stuck on an integral, just think what must have been differentiated to get that. Maybe you could work it back. Yeah. But also, it's like you also said, Rahat, that if you've got a line which has got a height of 2, the area under that is just going to be 2 times x, isn't it? Just a rectangle.
Mhm. So sorry, on a side note, to do with integration. So say if I was given a question, this large S, and then 2 with a 2 on top and 1 at the bottom. So then I do the same process. I get 2x plus c, and then you create those 2 separate brackets when you minus them from each other. So 2 in brackets 2 minus 2 in brackets 1, right?
Right, yeah,
And then you minus those from each other.
yeah, you find the area at 2. So what that would be the area at 2, which would be that much in purple. You find the area at 1, which is the area in blue.
And then you minus them from each other.
From each other, it'll tell you the area in between the 2, yeah.
Okay, so then that would be 2 in brackets 2 plus c minus 2 in brackets 1 plus c, and that should give you this area in between these 2 blue lines, right?
Yeah, exactly. Yeah, that's what
And then you add a plus c. Do you add a plus c at the end?
Well, I'll come back to that in a second. So if we look at the picture, you look at this first area, which is going to be 2 times 2, which is 4, and this second area is just going to be 2 times 1, which is 2. So just 4 take away 2 is 2. So the area here will be 2 square units.
Mhm.
Do you add a plus c? Yes, but it will cancel out because it'll be plus c minus c when you take away the.
Oh yeah, yeah. So plus c minus. Okay, yeah.
So my students tend to always add c, even though it's going to cancel, just because they don't forget. If you always add c, because people forget it, it's a well-known thing, and people forget plus c. So just never ever forget it by always doing it, and that means it will cancel out sometimes, but well, half the time. But so what? It cancels out. Great, you haven't forgotten it though, have you? So that's what I ask my students to do. Anyway,
Okay.
we were talking about a chain rule, but we've gone off a bit of a tangent, no pun intended.
Yep.
And we've got so far that to differentiate 2x is 2, but I would hope that you wouldn't actually differentiate that. You would know the gradient is 2, so you just write 2 down. So we differentiate 2x. Okay, now I need to differentiate sine, because the whole point of this is that we're differentiating this Russian doll, and we want to know the change of both sine and 2x. So we need to differentiate sine, but now sine has changed because it's become sine u, because 2x is u. So we differentiate sine u now. So we differentiate that, which is dy by du. And what's the derivative of sine?
Cos.
Yep. So there's a because u. Okay. So we have now differentiated both 2x and sine. So now we need to bring them together for our final answer, because we haven't actually got dy by dx here. We've got du by dx, and we've got dy by du. What we actually want is dy by dx. the derivative of y. Yeah. So if we look at what we have found, though, we've found dy by du, and we found du by dx, and both contain du, and they will, through division, just cancel out. That's the chain rule trick. The cancellation. We sort of differentiate two different things, bring them together, and those cancel out, and that leaves us with just the results dy by dx on the right hand side. So we just times it together. So we've got 2, which is du by dx times by cos u. And we can then replace the u with the 2x again. So the derivative of sine 2x is 2 cos 2x. Any questions?
So 2 cos u, okay. Okay, so we differentiate, we made 2x equal to u, we got 2. We made y equal to sin u, we got cos u.
Yeah.
And then we times dy by dx cos u. I'm trying to figure out how you got that 2 from. Oh no, sorry, it's just 2 times, okay, so just the derivative of one times the derivative of the other.
Right. That's it.
So
Okay. Yes.
what's the need for all this like workings out if you can just times the derivative of one with the other? Apart from obviously
yeah,
the
that's
u.
a good point. So you don't have to. I mean, it's so easy that you can just write the answer down. Yeah, and you're allowed to do that. It's called differentiation by inspection. Just write it down. Yeah. So if you want to do it super fast, just write it down. Okay, that's fine. That is acceptable. But I'm showing you the process of why it is that way. Yeah. If I just showed you the answer, you wouldn't know why, would you?
No.
Yeah. So, but in reality, we just go derivative of sine 2x is 2 cos 2x because differentiate 2x, differentiate cos sine cos. The thing inside stayed the same because inside the Russian doll. So 2x, remember, doesn't get affected. I said before, doesn't, because of times it by 2, nothing happens to it, so it just remains as 2x. We've painted the Russian doll times by 2, it's not doing anything. But the sine has become cos because that changes.
Mm-hmm.
So both of the things change. We increase both by a little bit, see what the change is. And the result is the product of the two. But don't get that confused with product rule. It's just the trick is we multiply them to get rid of the du's. And that's it. We've differentiated a composite function. Any other questions?
No question for me.
Okay, so let's do another one. The other suggestion was y equals e to the 2x. So we could probably do that without any by inspection. Can you tell me the answer straight away?
E2x.
Yeah, if we differentiate that.
But shouldn't it say this?
2e times 2x? Sorry, 2e to the power 2x?
Yeah, 2e to 2x. That's what it'll come out as. Yeah. What are you going to say, Ali?
Yeah, I thought something different.
Okay. So u is 2x. Differentiate that. That's obviously 2. That makes y equal e to the u because 2x is u. Differentiate that. Interesting thing about e to the u or e to the x or whatever, it doesn't change. Because at any point on the curve of e to the x or e to the u, its y coordinate is the same as its gradient, which is an odd thing. But there you go, so it's the same value. So for example, at 1, the y coordinate is e to the 1, but so is the gradient. So the higher the y value becomes, the higher the steeper the gradient becomes. So we have 2 times e to the u. So dy by dx is going to be those two multiplied together. Du by dx multiplied by dy by du. So that's just 2e to the u. And again, what's inside is not affected. So it's 2e to the 2x. So essentially, we just times the derivative of one by the derivative of the other. Derivative of one by the derivative of the other. And there's our answer.
So is there like any point in time where you would get confused between a composite function and a normal function? Because say for a normal function you'd use the product rule, right? Which is v du plus u dv, but for composite functions like this, you need to use the chain rule. Are there any like equations you need to look out for that might be a little confusing in the way that they're displayed? That might mean that you use the wrong rule.
I can't think of any, but we could get combinations. So we could get a chain rule, a composite function within a product rule. So you might be asked to differentiate, say, x sine 2x.
Okay, so that's x sine 2x. So that's x times sine 2x. So in that sense, it's a product rule, and then the x and then the sine 2x. That's the chain rule.
Yeah. So we've
So
got
you
yeah.
So you differentiate the sine 2x first, and then using the chain rule, and then use the product rule to find x times sine 2x.
Oh, very good. Yeah. So we've got a kind of composite differentiation because we've got to do a chain rule within product rule. Yeah. So it's like a composite of rules. Yeah. So first of all, the outside thing is that this is a product of two functions, x times sine 2x. Yeah. So that's product rule to us. But then within that, like in the Russian doll of rules, you've got to differentiate sine 2x. So do you want to both have a go at that for 2 minutes or 3? I'll say 3 minutes. So 10:43, and then I'll go through it. And we'll see if your answers match up.
So to find the v and you need to find the derivative of sine 2x, right?
Yeah,
That's v times the derivative of sine 2x, but you'd need to do the chain rule to find the derivative of sine 2x, right?
Precisely. Yeah.
Okay, so you need to do the chain rule first then, to find the derivative of sine 2x, so then you can use that for the chain rule.
For the product rule, exactly. Yeah, that's what I said. Exactly what I just said. Yeah. So we've got like a composite. You have to differentiate the sine 2x before we can even do the product rule. It's like a composite of rules. Share my screen. Okay, yeah. So start again, please.
So I labeled x as v, sine 2x as u, and
Okay.
as per v du plus u dv. V du is x times the derivative of u, which is 2 cos 2x,
Okay.
plus u dv, which is
Let me just
u
stop there.
sine 2.
Okay, yeah. Let me just start with that. It doesn't really matter about the order, but normally we do u then v. And for some reason we did v then u, but it doesn't really matter. But yeah, okay, yeah. So
u dv plus v du.
v du plus u dv, yeah.
That's the order I did.
Yeah, but then you did v then u, but it doesn't matter. It doesn't matter. But yeah, as long as you do VDU plus UDV, doesn't matter. Okay, yeah, so derivative of x is 1, so du by dx is 1, and derivative of sine 2x, as we already discovered, was 2 cos 2x. Yep.
So x times 2 cos 2x plus sin 2x times the derivative of x, which is 1. So 2 cos 2x x plus sin 2x, which is what I got.
Yes, it would, using my system, it'd be the other way around. So it'd be sine, so v du would be sine 2x, so v is sine 2x times by du is 1, plus udv, so it'd be x times by dv, which is 2 cos 2x. 2 cos 2x. So to simplify that a bit, we get sine 2x plus 2x cos 2x. We normally put it in order like that. So that,
2x cos 2x.
yeah, just the order, what you said is right, just the order we write it in is number.
Oh, okay. Sorry.
Okay.
So 2x plus
Sine 2x plus 2x cos 2x. Yeah,
okay.
so the left-hand side is sine 2x times by derivative of x, and the right-hand side is x times by the derivative of sine 2x, which is 2 cos 2x. That makes sense, Ollie?
Yeah.
Yeah. What did you do?
Oh, I just didn't do the sine 2x.
I didn't differentiate it, or
No. No.
okay. So you got, obviously, it's because it's a product. We're going to be, it's a product rule. So you differentiate both things and then times them together, times one by the other, another by it's like a cross thing. Yeah. So it's that times that plus that times that.
Yeah.
Yeah. Okay. So I've got a couple here to do. Both are composite functions contained within other rules. So do you want to have a go at those two for me? Shout out when you're ready. I'll just pause the recording. Going back to the screen each time, but there we go. So x squared cos 3x it is, isn't it? Yeah. So let's go back to scribble out. X squared cos 3x. Yes, x squared cos 3x. Okay, far away, Ollie.
So x squared cos x is a function as part of it. So if we differentiate that, we get minus 2x sine x.
Start again. I didn't get the first bit. It's what?
X squared cos x is one function.
No, definitely not.
Okay.
Because x squared times cos x is a product of two different types of function. This is a polynomial or quadratic. That's your favorite trigonometrical. But there's not one function. There's two things multiplied together. So what rule would we use to differentiate functions that are times each other?
That's the chain rule.
No, chain rule is for composite functions. These
Oh,
aren't product. Yeah, product rule. Yeah, product rule. So product just means times. It's just an old-fashioned word for times. So product rule, yeah. So we're going to be using this, but the problem is, what type of function is cos 3x?
It's composite.
It's a composite function, yeah. As is cos x. But cos 3x is even worse. So we differentiate both. And then multiply one by the other. That's it. So we need to differentiate cos 3x. So we need to differentiate x squared. So it'll become 2x, right? It's simple as that. And cos 3x, what would that become?
I got minus 3 sine 3x.
Yeah, so the cos differentiates to sine, minus sine. 3x differentiates to 3, so just times them all together. We get minus 3 sine, and the 3x is unaffected. So differentiate both, times them together. Derivative of 3x is 3, straight line. Derivative of cos of minus sine, times those together. So we've got everything we need now to put together for the product rule. So v du plus u dv. So v
So
du,
I got
yep,
cos 3x times 2x plus x squared times minus 3 sine 3x.
right. So 2x times cos 3x, because it's okay, it's v du, but we'd put the x term first. Plus u, doesn't matter which order we put them in.
2x cos 3x. So 2x cos 3x, would you add that?
That's right, yeah. So we wouldn't write cos 3x 2x because there might be some ambiguity that you times the 3x by 2x.
Okay, so that's x squared minus 3. And no.
And then x squared times by minus 3 sine 3x. So then we're going to put a plus there, but it'll become a minus 3x squared sine 3x. So we times the x squared by dv. So x squared, so u dv. X squared minus times by minus 3 sine 3x is minus 3x squared sine 3x.
Okay. Could you write that as minus sine x 3x x squared? Or is that wrong?
You could write that, but it's a danger of ambiguity. So it's not written. It's not wrong, but it's not written that way because if you wrote it like that, someone might think it's their times. It's just that. So what did you say? Minus 3 sine 3x x squared. Yeah, yeah. Oh, that's got to show it to you. That's, you'll never see that in the textbook because you go, oh, there's brackets means multiply, just times those together. There's a danger of ambiguity. So we'll put that there instead, and there's no chance that's what it means.
Mhm. Okay, so final answer is 2x cos 3x minus 3x squared sine 3x. Is that
That's
it?
it. That's it. Yeah.
Okay.
So because they're a product of function, two functions, you can't just differentiate them term by term and say that's the answer. We have to do this v du plus u dv crossover, and that'll give the correct answer. So if we do that, we differentiate x squared, we differentiate cos 3x, but cos 3x is a composite function. So got to use a chain rule for that. Use a chain rule, then we've got our answer. We've got our answers. We've got du 2x. We've got dv minus 3 sine 3x, and then we do this kind of crossover v du plus u dv. It's like the middle part of it is literally the middle part of a multiplication. That's why it has that crossover of feeling to it, because that's where it came from in the first place, multiplying those two things together. And yeah, that's our answer. V du plus u dv. So 2x cos 3x minus 3x squared sine 3x.
Okay. Okay, next question then.
Next question. Yeah, so that's just I always like to have a little backup. So let's have a look and see what Wolf and Alpha says. Differentiate x squared cos 3x. I feel like using Chat GPT using this because that does it all for you. Do my A-level example for me. Differentiate x squared cos 3x. There we go. So I'll give that a second to think about it. Let's make sure they match up. There we go. And the answer, according to this, is 2x. Well, 2x cos 3x, which is what's there. So it's written in, they're taking the x out, it's been factorized. 2x cos 3x, which is what there, yes. Minus 3x squared sine 3x, which is what we got there, yes. So yeah, they agree. That's good.
Okay. So one more thing regards to the second question. What's the derivative of log? That's a log, right, Ellen?
That's right. Log x, yeah. So what's the derivative of log x, Ollie?
So just log x.
Yeah, just log x.
Yeah. What does it differentiate to? Yeah.
Yeah, I thought it was just log x because it's a.
It stays the same. You differentiate it.
Right.
Okay, so it's the same.
No, it doesn't say the same. There's only one function that stays the same. What function stays the same when you differentiate it?
D.
What function stays the same when you differentiate it?
E.
E to the
X.
x, yeah. E doesn't. E is a number, so it'll become 0. E to the x, yes. So log x is not e to the x, so it's not going to stay the same. No. So what I'll do is I'll write down
1
three.
over log x, is it? Maybe.
I'll write down 3 possible answers, and then we'll take a vote. Okay. So it could be this. It could be this. Or it could be this. Which one? Choose door 1, 2, or 3. So Rahat, pick.
Two.
Okay.
I'll pick the middle one. 1 over x.
Right, yeah, and your choice is Ollie.
Yeah, I picked the same.
So what? They're both going for that?
Hmm.
Okay, why did you choose that one?
Don't know.
Okay, Rahat, why did you choose that one?
I don't know, something just told me it made sense.
Ah, okay, yeah. Ooh, and the winner is this one. No, just joking. It's this one. It is this one. Yeah, it's 1 over x.
Okay.
I won't go through the derivation of it now, but I will next lesson first thing. Okay, explain why it is that. Yeah, so dy by dx of log x is 1 over x.
That's all I needed, really. Okay, thanks.
And a little thing to know, if you integrate 1 over x, what does that become?
Add an x.
Back to itself, yeah. Plus
Let's see.
Okay, yeah, so have a go at that question. 3 minutes again, and I'll pause the recording. If I could figure out how to do that. So log x squared plus 1 over x squared plus 1. So here is the problem. Y equals log x squared plus 1 over x squared plus 1. U will be log x squared plus 1. V is x squared plus 1. So we've got to differentiate those, and then we're just going to do the cross. And this is the same cross from the multiplication cross that we have in the usual method, yeah? Right-hand column, cross, left-hand column. This is that is actually that cross. So let's differentiate v first. That's easy. It's just 2x. Okay, and then we want to differentiate log x squared plus 1. So that's going to be let u equal x squared plus 1. du is 2x. That means that technically I shouldn't really let u be equal to x plus 1 here because I used u here, but just for the purposes of this differentiation, I'm just going to cheat a bit.
Should I be seeing a screen right now?
Oh, I forgot to share it. Sorry, that would help, wouldn't it? Thanks for mentioning that. So I'll just backtrack a bit. Just skip through the videos this bit. So we have u is equal to log x squared plus 1. V is equal to x squared plus 1 because we're going to use the quotient rule here. Yeah, so this is u, this is v. I'll just label them to the right. U is log x squared plus 1. V is x squared plus 1. We're going to differentiate those, and then we're going to cross multiply. And like I said, it's the same cross that is within, you know, the usual right-hand column, cross, left-hand column. That's what this cross is. The same for the product rule. Yeah. So we'll differentiate v first. That's easy. So it's 2x. And then we've got to differentiate log x squared plus 1 as a composite function. So I'm going to let u equal x squared plus 1. So that's what I was saying here, that we shouldn't really use u because I'm using it for the function itself. But just within this little problem, I'm going to cheat a bit. Differentiate that. That's 2x. And then that means that it's it's log u. So differentiate that. It's 1 over u. So just got times 2x by 1 over u, which equals 2x over u. And this equals 2x over x squared plus 1. So there we
So
go.
what I got?
Is that what you
So I
got?
got 2x times 1 over x in brackets x squared plus 1. So what did I do wrong? So u equals, so yeah, x squared plus 1 equals u. Okay, you differentiate that, you get 2x. So then wouldn't you just times 2x by the derivative of log, and then times that by x squared plus 1? No?
No, because the x squared plus 1's in the Russian doll. It's not going to be affected.
Okay, so the derivative of log x is log over x squared plus 1.
Whoa, got some writing going on there, Ali.
Oh, sorry, was that me?
Yeah, you just graffiti in the place. Yeah, so derivative of log x is 1 over x.
Uh-huh.
So
Oh, okay. So in this case, the x squared plus 1 is the x.
yes.
Yeah, I didn't see. I put 1 over x times x squared plus 1.
No, because that's how the composite functions is that they're not affected. So
Okay,
what
that
happens
one's
is
wrong.
the derivative of that goes there, and that goes there. So if it's log x squared plus 1, the derivative of that goes there, and that goes there. That's basically what happens. So you can't see it. The derivative of it goes there, and that goes there. X goes there. X squared, log x squared plus 1. The derivative of that goes there. X squared plus 1 goes underneath, which is why that's the general result for that, to differentiate a log composite.
Okay, yeah. So 2x over x squared plus 1.
Yeah. So if it was a log 2x, it'll just become 2 over 2x, which is 1 over x. That actually goes back to 1 over x.
Okay. Yeah.
Okay.
So we found
So now we do a little cross thing. So we're going to do VDU, but minus because it's a division. So VDU is going to be, so let's just put DU in here at the top. 2x over x squared plus 1. All the way that. So let me just change the color here just to freshen it up a bit. So v du will be x squared plus 1 times, oh look, there's a nice cancellation. So v du is x squared plus 1 times by 2x over x squared plus 1. Yeah.
So like we just add 2x.
That will solve, that will reduce the x. Yeah. Minus udv, u is log, running out of room here, log x squared plus, just wipe this out of the way. Log x squared plus 1 times by du, sorry, dv, which is 2x. So we're going to have on the top there 2x minus 2x log of x squared plus 1 over v squared. And v is x squared plus 1, so it's x squared plus 1 squared. So v
Squared
du,
plus 1 squared.
yeah.
Oh, okay, that's where I went wrong. I wrote x plus 1 squared. So then I just like expanded it out to get x squared plus 2x plus 1. X squared plus 1.
If you did that, there'll be x to the 4 because it's x squared times x squared
Yeah.
plus 2x squared plus 1. Yeah. So
If
yeah,
you cancel, are you expected to simplify that x squared plus 1 squared? Or can you just leave it
be
like that?
simplified. Yeah. So remember, brackets mean multiply, but they also mean this expression is factorized. So we could multiply all that out, but it's just easier and simpler to leave it where it is.
Mm-hmm.
In fact, we could also factorize the top line. 2x is common, so 2x 1 minus log x squared plus 1 over x plus 1 squared. That'll be dy by dx. Yeah, so we're really doing some math now. Yeah, this is like, there isn't a number on the page now, just letters. Yeah, but it's not any different to anything else I've ever done, really. Just a cross multiplication of derivatives. So obviously we've got a bit, it's building up a bit, we've got to differentiate running parts. I would just times them together or taking them away or whatever. And then write them all down. We're just making sure we stick to that. And there we go. So any questions on that? Any other questions? Ollie, does that make sense?
Yeah, I'm gonna practice a lot today, I think.
Yeah, exactly. Yeah. Bit of familiarity with it. Yeah. Here's one I prepared earlier. So it's 2x 1 minus x squared over x plus 1 squared. So 2x, oh, the signs are the other way around, I think. Oh, it's just a minus sign there, that's all, that's why. So yeah, we got it right. So if we just change that around, 1 minus log x squared plus 1, that will make it work. So we got it correct. So the good thing is that if you're trying these today, Ollie, you know, you're practicing it, you can use that website to check your answers, or if you haven't got the answers available, it will tell you. Yeah.
Cool.
Not 100% perfect, but it will probably do you. Yeah. Okay. Any questions, guys?
No.
No. Just